Have you ever stopped to wonder what Python is really doing with your computer's memory? Well, today, we're going to solve a memory mystery that stumped some serious developers, and in the process, we'll reveal the secrets of what's happening under the hood every single time you run your code. Okay, so let's just dive right in with a real-world puzzle. This one actually came from a developer on Stack Overflow, and it is a fantastic case study that really peels back the layers of how Python works. So this person ran the exact same code in two different Python interpreters. You got the standard one, CPython, and then a high-performance alternative called PyPy. And the result? Well, it was genuinely shocking. Now, the speed part? That was no surprise. PyPy is built for performance. It's a beast. But the memory usage? Whoa, it was completely off the charts. And that just flies in the face of the idea that faster code is always more efficient. So what on earth is going on here? To understand why this happened, we can't just look at the code on the surface. Nope, we have to go deeper. We need to look under the hood at Python's fundamental memory architecture. And it all starts with understanding these two totally distinct worlds of memory that Python operates in. You've got the stack and you've got the heap. Okay, think of the stack as this super organized, neat freak workspace. Every time you call a function, Python puts a new little frame right on top of the stack, kind of like stacking plates. And when the function is done, bam, that plate gets popped right off. It's incredibly fast, super efficient, and it's all managed for you. The heap, on the other hand, that's where all the actual stuff lives. Your numbers, your strings, your big old lists, they're all stored here. It's more like a giant, less structured warehouse. So when you have a variable on the stack, it's really just a little label, a pointer, that points to the actual object living out in the heap. So this really breaks it down, right? The stack is for the quick, temporary stuff that's tied to your code's flow. It's all about speed. The heap is for the actual data, the objects themselves, which need to hang around for a while. This split, this is our first big clue to solving that memory mystery. So if all your objects are just piling up in this big heap warehouse, how does Python keep from just running out of memory? Well, it's got a really, really clever two-part strategy for that, a cleanup crew, if you will. Okay, the first and most common method is called reference counting. It's actually pretty simple. Every single object in Python has a little counter attached to it. Every time a new variable points to it, the count goes up by 1. When a variable goes away, the count goes down. And the moment that little counter hits 0, poof, the object's memory is instantly freed up. But there's a catch. What happens if two objects point to each other? Object A points to B, and object B points back to A. Well, now their reference counts will never, ever drop to 0 on their own, even if nothing else in your program can reach them. And that, my friends, is a memory leak, just waiting to happen. And that's where the second part of our cleanup crew comes in, the garbage collector. It's Python's safety net, and it periodically goes on a hunt for these cycles. And its strategy is brilliant. It's called a generational collector. It works on the idea that most objects die young, so all new objects start in generation 0, which gets checked all the time. If an object survives a few cleanups, it gets promoted to the next generation, which gets scanned less often. This lets Python focus its energy where it's needed most. Pretty smart, right? Okay, so now that we're armed with all this knowledge about the stack, the heap, and the cleanup crew, let's go back to our original mystery from Stack Overflow and figure out how to write way more memory-efficient code. And here it is, the smoking gun. The original code used this one little function, sys.stin.read. The problem is, that command tries to read the entire input file, in this case, a massive 110 megabyte file, and load it all into memory as one giant string. And the fix? Oh, it is so simple, it's beautiful. Instead of trying to read the whole file at once, you just change the code to use an iterator. This version processes the file one line at a time. It only ever holds a single line in memory at any given moment, which completely slashes the program's memory footprint. I mean, just look at that difference. It is absolutely staggering. With CPython, the bad way used over 200 megabytes of RAM. The iterator method? Just 7. And that finally solves our PyPy puzzle. The thing that makes PyPy so fast, its just-in-time compiler, needs its own memory to work its magic. So when you feed it inefficient code that's already a memory hog, that overhead gets magnified. But when you fix the code with an iterator, both interpreters become super lean and efficient. And you can apply this kind of thinking everywhere in your code. So instead of building a massive list that eats up all your RAM, use a generator that just gives you values as you need them. Or if you're creating thousands of objects from a class, using underscore underscore slots can dramatically shrink how much memory each one takes up. Speaking of efficiency, Python has another awesome trick up its sleeve. This one isn't just about memory, it's about speed. Let's take a quick look at how it handles your actual code files to make them run faster. See, Python is smart. It's not going to reread and reinterpret your human-readable source code from scratch every single time you run it. That'd be way too slow. So the first time you run a script, it compiles your .py file into a much faster, lower-level format called bytecode and saves it as a .pyc file. And of course, Python is smart about this too. It has to know if you've actually changed your original code, right? So it has a few ways of checking. The default is to just look at the file's timestamp. But for more complex projects, you can tell it to be extra careful and compare a unique fingerprint or a hash of the file's contents. So you see, peering under the hood of Python isn't just some academic exercise. Understanding that dance between the stack and the heap, knowing what the garbage collector is doing, it gives you direct control over your code's performance. You can write programs that aren't just faster, but are way smarter and more reliable. So the real question is, after seeing all this, what are you going to go optimize first?